Science 30. Sorry, I had a little technical difficulty with my calculator. The battery's conked out. So the answer that we're looking for here, right energy equals Q times V. It's going to be 15 coulombs times right, so it was 1.5 times 10 to the 8th volts times 15 coulombs. So voltage times charge, and we get an answer of what have we got? 1, 2, 3, 4, 2.25 times 10 to the 9th joules. So this gives us an answer of 2.25 times 10 to the 9th joules. So that's in one lightning strike. The average Alberta household uses 3.0 times 10 to the 9th joules of electricity every month. So if you compare, it's close, right? So a single lightning strike is reasonably close to the same amount of energy that you would use in your home for a month. Okay. Let's just see here if I can give you some questions related to coulombs. Okay, so none of those questions are relevant just yet. All right, so I'm going to continue on with this lesson here. So we talked about electric field strength, directions of electric fields, thunderstorms. Magnetic fields is the next big field that we're going to look at. So it's the property of the space around a magnet or current that enables the magnet or electric current to exert forces on other magnets. So if something is in the area of this magnetic field, it will be under the influence of this magnetic force. Okay? This magnetic field lab, you guys can do. Okay, so when you know how to draw magnetic field lines, normally we would use magnets in class, but you're not going to be able to do that because we are not in class. If you have magnets at home, you can mess around with them a bit if you want, I guess. You need to draw the field lines. And you can answer these questions with this lab. So you should be able to explain these answers 6, 7 after I look at magnetic fields and gravitational fields. The notes here talk about permanent magnets and electromagnets. Read through those. You can do that field lab, on your own time. Now, when we look at magnetic field lines, as you can see, magnetic field lines always go from north to south. Okay, so the magnetic force is exerted along the lines of the magnetic field from north to south. Now, we can have two types of magnets. There's a ferromagnet which is created by metals that are oriented in the same direction. So the molecules are oriented in the same direction. And we can have electromagnets where an electric field is moving, so electrons are moving. When electrons move, they create a perpendicular magnetic field. So it's actually electrons that create magnetism. I'm not going to talk a ton about it because it has to do with quantum mechanics. But you can do a little bit of research more into it. It's quantum mechanics, when you talk about electromagnetism, is really fascinating. Right, so but you have ferromagnets, which are stationary metals. All the electrons are oriented in the same direction. But when we look at electromagnetism and magnetism itself, moving electrons create electric current, and they create a perpendicular magnetic field. So this is an electromagnetic wave. You will have electrons moving in one orientation, and there's always a perpendicular magnetic field, right? So sunlight, ultraviolet radiation, any type of electromagnetic wave, like a radio wave, or a microwave that we use for communications, this is how it works. Electrons moving with a magnetic field in a perpendicular direction. So you can see the direction of the field, the magnetic force is, right, so the magnetic force and the the electric field and the magnetic force are in perpendicular directions. So this is called the left-hand rule, and if you were to sort of create, if you were to, use your thumb and index finger and middle finger and move it like this, the direction would be my index finger of the movement. Okay, the electric field is my thumb, and the magnetic field is my middle finger. So this is all moving in this direction, but the electric field and the magnetic field are perpendicular to each other. So when moving, electrons actually cause magnetism due to angular momentum. Now this is called electron spin. So think of electrons as a flowing loop of charge. So they're not only moving, but they spin at the same time. And when they spin, they influence the molecules around them. And this shows you this right here. So these are electrons, and electrons can spin in either direction. This is not a physical spin, it's a quantum reality. And again, I'm not going to get into huge detail about that in Science 30, but the electron not only moves, but it also orbits around its quantized energy field, and that spin is what actually creates the magnetism. All right, so there's an electromagnet with electrons moving. So this is ferromagnetism, right? So ferro, right, iron. Iron is a very good ferromagnet. So some objects are not moving. Not moving also have magnetic properties. Horseshoe magnets are objects that contain metals with magnetic properties like iron. Metals with magnetic properties have areas on them called domains. So these regions of matter that are divided are called domains. And when you have a ferromagnet, all the domains are lined up in the same directions. So the electrons are all spinning in the same direction, and that creates the magnetism. So you could magnetize a ferromagnet by moving it through an electromagnet. Okay? So the domains align, and the protons and electrons in a ferromagnet are influenced by the angular momentum of the applied magnetic field. And you can move the molecules within the ferromagnet to be oriented in the same direction, and that will create magnetism. So moving charge can create magnetism. Moving charge is called current, right? So Earth is a big magnet, right? It has a molten iron core. So if you look at your first right, if you look at the first piece on this magnetic field, field lines are always drawn coming from the north, going to the South Pole. Right, so if I were to draw this, it would kind of look like that. Again, the field lines here they would repel. These are like field lines, but the arrows are leaving the North Pole. They would be going towards the South Pole on this magnet here. So you would draw that with the arrows pointing towards the south. Horseshoe magnets, right? I could have a north and a south pole. Right, so you guys can draw your field lines according to that as well, right? Field lines will go around the magnet and within the magnet as well, right? So you would have attraction this way. You would have attraction going this way as well on a horseshoe magnet. Okay, so the field lines always go from north to south in a magnet. So you have lots of... So here's a couple, right? So I looked at the left-hand rule, right? You have direction, electric force, and magnetic force, right? So this is why magnetic force is 3D, because there has to be the direction of the electrons moving, and when that happens, you create electricity and you create magnetism. So you create forces in 3 directions. Some of this is just a bit of a thought lab for you. Question 1 here, right? Like charges repel, unlike charges attract. You can rephrase that applying to magnetic poles, right? We don't have charges with magnetism, but we have like poles and unlike poles. Okay? So you should figure that out. I'm going to talk about gravitational fields in a little bit here. But the Earth itself, right, has an iron molten core and spins on its axis, so it has a magnetic field. Okay. Now the interesting thing about the Earth, if I were to draw this on my board, right, so we have the Earth and it spins on its axis at 23.5 degrees, right? You have a North Pole, and then you have a magnetic north, right? So if you look at a compass, right, you know, the actual arrows point towards magnetic north. So magnetic north is not at the center of the axis, right? Magnetic north points this way because it points towards the axis, right? The magnetic field is tilted on its axis. Okay, but field lines, so here's what happens though, right? So we know that when we look at the Earth, the magnetic field lines point towards north. So magnetic field lines actually go this direction. So the compasses, when they point towards magnetic north. But I just told you that field lines always go from north to south. So when we look at our geographical and magnetic north are not the same on Earth. So they are not the same. Right, so our magnetic south is actually our geographical north. So right now, this is actually, the North Pole is magnetic south. Because our field lines go from, always go from the North Pole to the South Pole. So our compasses follow the magnetic field lines of the Earth and point to geographical north, which is actually our magnetic south pole right now. Okay, so this is Earth. This is really important because all of our, GPS systems and GIS systems, our satellite orbits depend on the magnetic field, and all of our telecommunications are dependent on the magnetic fields of the Earth. So this is important for us to understand. So Earth's magnetic field is a result of moving charges because we have a liquid outer core and we have a molten iron core we have, iron moving and creating electromagnetism in the middle of our core. Right, so our field lines always point towards magnetic south. But the Earth is spinning. So what happens over time is, right, so layers of charge can build up. As a result, as Earth spins on its axis, this liquid outer core creates a terrestrial magnetic field. So compass needles always point towards the south pole of a magnet. This magnetic south pole of Earth is actually in the northern hemisphere. So when a compass points north, it is pointing to our geographical north, but it's pointing to its magnetic south. So magnetic south is actually geographical north. So here's the deal though, Earth is always rotating. So these field lines, they can bend and twist and get messed up. Okay, and then the field lines break and then reform. This is kind of what happens on the sun when we get sunspots. Is because of the metals inside the sun that are vaporized, they create magnetism from the moving electrons. And what that does is it creates a magnetic field that's constantly changing. And when the magnetic field bends and twists, the sunspots move along that. This is part of what that has caused some climate change over the long term. So here's the deal, right? Earth's magnetic poles flip on average about every 450,000 years. So their rotation will mess those magnetic field lines up and they break. And then the poles flip after that happens. So the last major flip was about 780,000 years ago. So we are overdue for another pole flip. So when the poles flip, when geographical south becomes magnetic south, all of our telecommunication systems might be messed up because of that. So that's really important when you think about how the internet functions, for example, right? So Earth's magnetic field is created by moving charge from molten iron and other metals flowing inside the core. As the Earth rotates, wind gets deflected, and those are called Coriolis forces. So particles get deflected because of the rotation of the Earth. So if I'm like firing a rocket, for example, I not only need to account for the destination where I'm going to, but I also have to account for the speed and the rotation of the Earth to keep it on its course. So rocket science is, actually pretty complex. Right, so Coriolis forces cause deflection of flowing particles due to Earth's spherical nature and rotation on its axis. And this influences fluid dynamics of the molten outer core of the Earth. So disturbances such as, the tectonic plate shifting or asteroids impacting the Earth can disrupt the electrical currents that are happening in the molten iron core. Those can cause pole flips. And then the natural rotation of the Earth can also cause that as well. So the field lines become twisted, and this weakens the field strength and can cause the lines to break and realign. So how do we know this happens? So let's talk about the magnetic field just in general with Earth's magnetic field. So this is the Earth right here, and these are its magnetic field lines. Okay, so think of it kind of moving. When we look at the magnetic field lines, Earth's moving through the medium of space, and there's particles. There's ionizing particles, radiation and charged particles coming from the sun and from other celestial objects. The magnetic field, what it does is it helps us, right? So we have the ionosphere and the magnetosphere as part of our part of our spheres of the atmosphere. The magnetic field, what it will do is absorb a lot of that ionizing radiation, and it protects us from, being bombarded with X-rays and gamma rays. But just like a kind of a boat moving through water, there's entrails in the wake, and these particles kind of can move through there. All right, and this is an area like as the Earth moves, as we move through radiation and we move through particulate in the atmosphere, this stuff can get burned up, And this is where the northern lights happen. Okay. So the Earth's magnetic field helps protect us from cosmic rays and solar winds. Solar winds are, streams of particles like, potassium and hydrogen ions and things like that coming from the sun. It deflects most high energy ions, so our bodies are not bombarded with charged particles, which can cause mutation. Right, so cosmic rays and solar winds contain high amounts of electrons and protons, right? So some of the solar wind gets through the magnetic field through polar cusps. If the solar wind gets into the atmosphere, they collide with atmospheric particles and cause the aurora borealis. So that's kind of cool. So, right, these are the northern lights. You can see them, on occasion in Alberta. This is at Abraham Lake, and it's right, it's in Banff. If you take the road that gets you to Abraham Lake from the Icefields Parkway, you'll end up in Nordegg. So these electrons that cause the aurora borealis, or the northern lights, come from solar winds. And they contain different particles, and they burn up in the atmosphere, and they get caught in those sort of the wake of the Earth moving through space. They get heated up and they burn, right? So nitrogen burns purple. That's what causes the purple color with the auroras. Red and green light comes with collisions from oxygen. Now, solar winds, because they're charged particles, they can really disrupt the Earth's magnetic field, right? And that can disrupt cellular transmission, GPS. So if we have really strong solar winds in a place like Whitehorse, for example, in the Yukon, it might be tough for planes to land, right? Power surges, blackouts. Okay, so that's magnetic fields. I'm going to end these two lessons there, and I'll continue on with gravitational fields in another video. So I will continue this in a little bit.